Good morning, class. This is Professor Burke. We'll go ahead and do a recording of the first lecture in the class, Cybersecurity Concepts and Fundamental IT Concepts Review. This is intended to be kind of a quick review. I'm not going to deep dive into these topics, but it's intended for those who might have missed class to give them a little bit of context of what we went through. If you have doubts or questions about something on the chart, either contact me or look it up. Just go ahead and look it up. This is, again, intended to be an overview presentation. I'm going to do a compressed version so the recording isn't too long. Here are the things we'll cover. We'll go through some fundamental cyber concepts so you're familiar with the concepts and the vocabulary. Many of these are covered in more depth in other classes. But here it's just to build a fundamental, if you will, vocabulary and set of concepts as we get ready for Info 393 network security. We'll go into numbering systems and how you encode data in a system. The objective there is when you see data, you can recognize its formats. There are some, if you will, indicators in the character strings and what's being used, uppercase, lowercase, special characters that'll help you figure out what kind of data format it is, and then potentially you can cut and paste that data into a decoding, a conversion tool online and see what the data is in a format that's more user-friendly. We'll go into some simple concepts in cryptography. Cryptography is a whole subject covered in the Info 391 class in the fall, but we want you to see some simple forms of cryptography, which is encrypting data, and maybe how to recognize what encrypted data looks like. Finally, we'll go into hashing. Hashing's different from cryptography. We'll get into that in great detail. In this class, we really want to point out our focus is to understand risk by looking at all types of different variables. What are the threats and who are the threat actors and how are they motivated? What assets are we trying to protect and what's their value? Risk could be very low if we're trying to protect things of low or no value. What are the vulnerabilities? Which are the weaknesses that we might have within our cyber infrastructure? From that, we can calculate the risk. And the risk is a probability. It's probability times impact. We'll talk about that in a second. And then an exploit is when a threat actor or something bad happens, which actually takes advantage of a vulnerability and potentially can cause loss or damage to an asset. So there is an exploit. We'll also get into some other terms. What's the avenue or the attack surface for exploits? So these are some of the variables that we have to keep an eye on. I'm going to go into each one in a little more detail. All right, an asset has value. A threat is something that could potentially cause a loss to an asset. It could be an individual. It could be a natural occurrence like bad weather, hurricanes, power outages, influenza. It also could be, many of these are not malicious. A threat could be an employee or student accidentally does something, accidentally deletes a file, accidentally unplugs something that causes loss of data. So there are a lot of threats that are just, humans doing things that accidentally cause damage. Vulnerability is a weakness. So now we look at the system side. Do you have your antivirus software? Do you have a strong password? If you don't, you have a vulnerability. Do you let people use your devices, your computers, and things like that? Do you share your passwords? So there are all kinds of weaknesses in the system that could potentially allow a threat to exploit or cause damage to your asset. The risk is the probability. And I say the probability times the impact. So risk could be high, medium, low, based on how probable is a bad thing going to happen and what would the impact of a bad thing happening be. For example, if we have bad weather every month, I mean severe thunderstorms, and it seems almost every month we lose power at least once a month. and we work in a hospital. And when we lose power, we have life-threatening scenarios. Ventilators and emergency equipment don't run. So our risk is high. Now, same scenario, same, if you will, locale, maybe in the dorm room. If you lose power in your dormitory room, the risk may be low because you pivot and you go to an area that does have power, or you have battery backup on some of your devices, and you don't have life, if you will, life-threatening scenarios in place. All right, the exploit is taking advantage of it. That's where the threat takes advantage of the vulnerability and potentially caused loss or damage to the asset. Then finally, the attack surface. This is the vector, the if you will, the gateway, the pathway that the threat, the bad actor, uses to attack, to damage your asset, to exploit, excuse me, your asset. When you determine your risk, high, medium, low, you have 4 responses. One, you could avoid the risk. For example, if power outages is severe, you're a hospital, maybe you avoid it by shutting the hospital down. You don't take patients. I don't know, that's unreasonable, but there are things, you know, if the risk is, hey, planes go down, maybe once every 20 years a plane will go down, you don't fly, right? But you eliminate the cause. You don't do what potentially could allow the bad thing to happen. Okay, mitigate. This is where you take action, and this is what we see in cyber. And oftentimes, what would a reasonable person do? For example, a hospital, it would be very reasonable that they have redundant power sources and battery backups and emergency generators and all of the above, especially in the life-threatening spaces, the emergency room, the critical care unit, and so on. So reasonable action to reduce the risk is called mitigation. You could also transfer the risk. Instead of saying, hey, I'm not going to really do anything, but should that bad thing happen, I'm going to buy insurance. So a third party essentially is responsible. I'm just going to have extra insurance. I'll pay people off, and that's how we will recover and respond to the risk. So transfer. Finally, you can accept the risk, especially if the risk is low or reasonable. Again, the probability might be low or the impact is low. You just accept it. You might need just to have a contingency plan. Hey, if the power goes down, I'm in the dorm room, I'll just deal with it. I'll just deal with it. Or I already know I go up to Blackbird because they seem never to lose power. I have a backup plan. Attack vectors. Again, now that we know we have these threats and vulnerabilities, and we have potentially a threat could try to exploit a vulnerability, what's their avenue for attack? And think of this as, what's the perimeter? How does the attack start or get in to what we're trying to protect, or to the asset? What we want to highlight here is the primary attack vector is people. Typically, somebody is tricked via email, via a voice, a scam call on your telephone, your mobile device, and all the above. You're tricked, you're coerced, you're enticed, you are all the above. And we'll talk about that in separate sections, but typically it's an individual. So they are part of the attack vector, the attack surface. Now, the actual vector may be that it came in via email to an individual, or it came in via a phone call. So the attack surface might be phone, email, but typically the network is involved because the threat is usually outside of our internal organization, and it's trying to get inside into the, if you will, through the perimeter of the network. Okay. You can look at this chart, but the attack vectors or attack surface should be pretty clear. All right. Key security concept is what's called the CIA triad: confidentiality, integrity, and availability. When a cyber incident occurs, we want to look at it immediately, or when we have a vulnerability, or when we have a risk. What is the risk in terms of cybersecurity? do we have a risk of confidentiality being exposed, which is secrecy, that there is data, maybe we have top secret data, and we do not need, want, or we cannot allow individuals to see the data. We have to maintain confidentiality. Now, later on, we'll talk about cryptography. Frequently and normally, confidentiality means we have to encrypt our data, or we have to lock things up. We have to lock rooms up. We have to lock our desk up. We have to use strong passwords. We encrypt the data. There are all kinds of actions to make sure we keep our information, our data, secret, confidential. Integrity is different. This is where we have to make sure our data or our assets aren't maliciously altered or changed. For example, we got to make sure no one is getting into your bank account and changing the values up or down in your bank account. So integrity is about keeping data in its current, original, proper state. Do not allow data, information, or assets to be modified in an unauthorized manner. Then availability is simply, we need to make sure our services, our information is available. For an attack example here might be Netflix. Bad guys attack Netflix with, if you will, incredible volumes of requests and connections and all kind of other traffic to take down their streaming servers. So availability is about basically keeping your servers up and running, your data up and running. And also, should there be an attack, should that data be compromised, the integrity of the data be compromised, that you have backups, recovery mechanisms to get back up and running and be available. So oftentimes in availability, you have to have resilience, backups, fallover plans, redundancy, things like that, and firewalls, protection from the bad guys who are trying to overwhelm your services. All right. Another concept is in identity is called AAA. Okay. When we're doing identity, there are three concepts, and there are more, but three primary concepts. We have to authenticate. Who are you? So when you come in to use a system or an asset, we need to authenticate who you are. So that's authentication. Who are you? Authorization is the second question. What can you do? What are you authorized to do? And then finally, accounting is what did you do? We need to keep logs, tracking tables of audit records, and so on. When somebody got in and they altered the data, we need an audit record of who altered the data. So this is AAA. We might give you scenarios. You need to know which of the elements of AAA is in play. Okay. Layered security. And the second chart's probably going to be more, but in an organization, in a technical infrastructure, there will be multiple layers of security in place. This chart is less helpful as the next one. I'll go to the next one. Here we go. There are things that we do on the outer layer, and typically that involves the users, the end users, the people, because they are our biggest challenge. That's our biggest weakness. So we need to train them. We need to have policies and procedures. We need to have controls in place. All the way through to the center layers of defense is where we protect our data. That's where we have our encryption and our passwords. Right. So that's layers of defense. You can look that up, but essentially the people are on the outer ring, and policies, trainings, and administrative things have to be done to make sure people are aware of what they need to do, their responsibilities, the type of cyber hygiene they need to maintain. And at the center of the circle is the data, the hard technical, because that's at the center is what we're trying to protect. Most vulnerable is at the outer perimeter. Least vulnerable is at the center. All right. Now we're going to go into numbering systems, followed by hashing and recording. Excuse me, numbering systems and encoding. At its core, computers are based on binary encoding, which is zeros and one. That aligns to a electronic circuit where the circuit is either open, one, or closed, zero. So essentially everything in a computer system is going to be some derivative of base two, 0, 1. However, binary ones and zeros are not user-friendly, and most applications are not designed to accept binary. So what is happening within the system is those binary data representations are being converted into other numbering systems or data formats that are more user-friendly and more efficient to use within a system. So numbering systems and computer encoding is basically putting character data, which started binary, into some other format that is more efficient and user-friendly. This is not encryption. This is not about secrecy. This is about efficiency and compatibility within the system. So we're going to go through the basic numbering systems and encoding characters. First, the numbering systems. Binary, we already talked about. You can look this up, zeros and one. We are not a math class, but do know that 1 byte of data can represent up to 255, if you will, decimal characters, 250 from 0 to 255. You'll notice in computers, everything is some derivative of base 2. When you buy a computer, you get not 200 megabytes or 200 gigabytes, you get 256 gigabytes of memory. You get 512, you get 64. So those are basically the stair steps, if you will, in numbering systems in terms of units of data, units of memory within a computer system. Well, we got binary, we have octal, which is base 8. You recognize that with 0 to 7, that's 8 characters. Base 8, 0 to 7. If it has more, if it has an 8 or a 9, or if it has an alpha, it cannot be octal. Decimal, 0 to 9, that's 10 characters, because remember, 0 is a number. 0 is a number. Hexadecimal is 0 to 9, A to F. Hexadecimal is base 16. So you go 0 to 9. The number 10 in hexadecimal, decimal 10, is an alpha. The number 11 is beta, B. Charlie, C, is 12, and so on, all the way up to the number 15, which is F. So it's base 16, 0 to base 16, but the characters are 0 to 9, A to F, representing the decimal numbers 0 to 15. You'll see the table to the right. One thing I want to point out about hexadecimal in a computer system, frequently it will have a prefix of 0x, 0x, and then the hexadecimal characters. The 0x is not part of the number. It's just a prefix, blah. So when you see 0x and some string of characters, you cut and paste the data that's behind the 0x, put it in a decoder to translate it from hexadecimal to some other data format. Base 32 and base 64. Base 32 essentially is where each character can represent up to 32 different characters. So it's all uppercase, you got 26, and selected digits and padding. Frequently base 32 and base 64, you'll see padding, which are the equal signs. The equal signs are not part of the number, but you paste it all in, it's like a null. Equal is like a null, it's just a pad added to the number. Difference between base 32 and base 64 is base 64 is upper and lowercase. So if you see a string of characters, upper and lowercase and numeric, and you see that padding, those equal signs, it's probably base 64. If it's all uppercase with that padding and numerics, uppercase and numerics, it's probably base 32. Base 64 is very popular. You don't really see base 32 much. So in terms of popularity, you're going to see binary, decimal, hexadecimal, and base 64. Rarely will you see octal or base 32. Okay, ASCII. This is how do we get from all these numbering systems to text, human readable text? Well, ASCII is the character set, the American Standard Character Code, code for the information interchange. Blah. It is an English keyboard, if you will. Think of it that way. It is the English keyboard. It's the 128 characters on your keyboards, uppercase, lowercase, special characters, and so on. That is ASCII. Frequently, what you need to do is you may have a string of numbers. Those numbers actually represent text characters, because I'll show you on the next chart, every ASCII character has a corresponding hexadecimal or decimal value. So frequently we need to convert from the hexadecimal decimal values to ASCII so we can read the message, if it is a message. Unicode is basically the same thing as ASCII, but it's the universal character set. So it incorporates all of ASCII, which is 128 characters, plus additional international characters, maybe kanji characters, things like that, that take it up to 256. So when you see ASCII or Unicode, essentially it's human readable text. ASCII is a subset of Unicode. Unicode has 256 total characters, where ASCII is 128, which is your keyboard. And here's a table. So you may, at any given point in time, be given a decimal value, a hexadecimal value, a binary value, whatever. It corresponds to a character. For example, if I look at character decimal value 70, 70, 70, or hexadecimal value 46, that is capital F. That is capital F. So long story short, take these values. There are, in your browser, go to Google, find an encoding, decoding, translating tool for decimal to ASCII, hexadecimal to ASCII, whatever to ASCII. Plug your value in the tool. It'll give you back the ASCII string. Okay. Now, cryptography. Again, when we talked about the CIA, the triad, there's secrecy, which is done with encryption. There's integrity, which is done with hashing. We'll talk about that next. And then there's availability, and there are other things we do to ensure availability or recover for availability, like data backups and things like that. Right now, we're going to talk about secrecy, which is cryptography. I'm going to do just a quick verb on classical. There's a whole section on modern cryptography. By definition, it's supposed to be hard. You're not supposed to be able to crack the code, decrypt the data if you don't have the appropriate key, secret keys, or tools, authorities. So I do want to point out the difference. Encryption or cryptography is where we're trying to keep the information secret. Hashing, which we'll do later, is we want to have a way to double check to make sure the information has integrity. It has not been changed. So we do that with a hash. It's like a separate unique ID that has to balance. Okay, so let's do it encryption first. And I'm going to go down through a couple of key elements. In encryption, you'll have plain text, which is the original message. We will attack at dawn. You will use various methods to get to ciphertext, which is the encrypted text, a gobbledygook of characters or whatever. There will be some secret key that takes you from the plain text to the ciphertext. And way down at the bottom, you'll have the cipher or the algorithm you use. So oftentimes, if you know 2 or 3 of these, you might be able, through various techniques, to figure out the message. For example, if you know the cipher or the algorithm, the cipher, and you have the plain text, and you have a copy of the ciphertext, you use all those together, and the power of computing, you might be able to figure the key out. So the more information you have, the better, because that's the technique that's used. Take as much information as you can, and then you might, even through multiple iterations, trial and error, see if we can figure out the secret key, if we can figure out, you know, how to decrypt the data. All right. So classical cryptography was pre-computer. We'll show you a quick example. Modern cryptography, we'll do that in a separate class, or we'll integrate it into our class in a separate section. Today, and what's on the quiz is only some concepts from classical cryptography. Now, I do want to show you that there are two basic forms. There's a substitution cipher, a substitution algorithm, and a transposition algorithm. And quickly or simply put, a substitution algorithm says there is a string of characters, letters, characters, whatever, and you, based on some secret algorithm and key, will substitute every one of them, into a message, into a string of characters that is human readable. So basically, you're substituting. For example, if you have a message, an encrypted message that has A, that may actually get substituted with a Z. A B gets substituted with a Y. So you're substituting out what's in the ciphertext. Transposition is different, where all the letters are there in front of you, but they are not organized in an order, in a stream, or whatnot that is human readable. So a transposition cipher is we have to reorder the letters that are in front of you into the readable message. And for example, we read left to right. The message may be written right to left, up to down, diagonally. So there are various old-fashioned techniques that are obsolete that are used to see a secret message in what you think is unreadable lettering. All right. So I put a couple examples here. When we do our cyber competition, we're going to do a practice competition. You'll see examples. You'll enjoy that. This is probably fun. But the key is, if you know what cipher is being used, there are tools that through trial and error will help us kind of pound out what this message might be. So really the trick is to figure out what cipher might be in play here. And I'll show you, outside of this presentation, some techniques there. Let me do a quick example of a cipher. The second one on the list is called ROT 13 or Caesar. These are all shift ciphers. And in the old days, in the Roman days, in the Greek days, very few people read. So very few people, so I think only maybe 10% of people would even read. So if you wrote something down, most people couldn't read it. But number two, you may simply write your message, and then your encrypted version is a shift. So an A shifts 3 letters to the right, three letters to the right. And when you send the message out, a D is on the encrypted text when in fact it's an A. So it's a 3-letter shift consistently. This had to do with a physical, like, rotation device. A Caesar cipher and a ROT, which is a rotation, is a shift. Now you have here ROT 13, but it could be ROT 3, ROT 5, ROT 4, ROT 26. They are all, if you will, a shift based on how many positions in the alphabet are we moving. Okay. All right. I'm not going to go through others. There's transposition. Let's pick this up when we do some practice exercises. Okay. Now, one thing I do want to talk about, quick comment, is how do you make a cipher stronger? A couple of things. You use a more complicated algorithm. That's one way. You use a longer key. Instead of the key being shift 3, maybe the shift is 3000. You shift and around the alphabet, multiple iterations. So use a more complicated algorithm, or you use a longer key. Those are two techniques. We'll pick those up later. That helps make it harder to figure out the key the longer it is. All right. I'm going to keep it moving. There's some examples of substitution cipher, and then rail fence. Rail fence is a transposition cipher, but here, where you, instead of reading left to right, you actually read kind of diagonally down and diagonally up and down and up. And there are tools that help you do this, so you don't have to try to figure this out manually. If you put it in a decoder and you say, I want to take this message, this ciphertext, and do a 3-level rail fence, it'll lay it out for you. Right. We gave some examples. You'll have some practice examples in your assignments. Please take a look, do some research, and see how that helps. And then let's next get into hashing. And there's a hash example, but let me just talk about what hashing is. Hashing is very important. Again, hashing is for integrity. Did our data, as it's gone through its network transfers, its loading, its use, its processing, did it get changed in, was there any unauthorized changes to our data? So what we do, we have an algorithm that takes our data, and maybe it's a message, and it creates a separate unique identifier for that message. So you put your message in, an algorithm is used to create a string of characters called a hash. Okay, it is a one-way formula. You can't go from the hash back to the message. So anybody could see the hash and not know what the input message was. So that's key. One way, not reversible. Frequently on a system, we will load passwords as hashes. And basically what we're doing is we're loading the unique identifier for the password in the system. And we can check to make sure the password wasn't altered if there was any unauthorized altering of the password. So passwords are frequently stored on a system as a hash, a unique value. That means people could go look at it. They still don't know what the plain text password is. They just know the unique identifier. Okay. So it's used to check for integrity in the popular formats. If you see MD5, it's called Message Digest 5, SHA, and some others, but MD5 and SHA are two, if you will, key families of hashes. There are tools online where if you have a input, it could be an input file, it could be text, as long as it's data. It could be a picture. You can hash a picture. You can hash audio. You can hash anything that is at its core data. At its core data. So I tag some resources. There are tools you can use to generate hashes. There are tools to identify the hash. Is it an MD5? Is it a SHA? Then there's something called CrackStation. The only way to go backwards on a hash, as I said, it's non-reversible. It's one way, unless there's been a data breach or a data compromise. In that case, there is in the public domain a whole bunch of, if you will, messages and potentially passwords, usually, that have been compromised, and the corresponding hash is there. CrackStation will take and run whatever hash you have against that database of compromised passwords. And it'll tell you what the password, at least what that database of compromised passwords has. So CrackStation, if the password has been cracked, compromised, it will be in that database, and you can use this tool called online. It's called CrackStation online. Okay. And then there are other commands we use. We'll do that separately when we talk about password cracking, and that's mostly in another class. Hash is used to check identity, integrity. By the way, a hash oftentimes in the technology world is also called a checksum. A checksum is a hash. So, how do we make hashes harder and more complicated? Something called salt, where, for example, we have a password. We will add in part of our algorithm some random characters to the password. If your password is Apple, I'm going to add random characters, otherwise known as salt, as I create the hash. By making the message input, if you will, more complicated and more unpredictable, I store a hash that, one, should be more unique, and also should be more unique. We don't want two hashes. You'd have the same hash as somebody else who's using the password Apple. So we're trying to make the input data more random. There we go, more unique. So salt is a way to make a hash more unique, more random. It is put in before you create the hash, not after, before you run the algorithm. And that's it. Encryption is confidentiality.
hashing is for integrity. You're going to see you're going to see both a lot, encrypted data, and you're going to see hash data. Um, and you're going to use hash data. Oftentimes, you will use that to make sure the source data file, picture, audio, whatever, has not been modified, that the current hash for that file matches the original hash that was created for that file. Okay. And I'll pause there. There's more information, but we get into this when we do our cryptography module in the Info 391 class. Guys, thank you. If there are questions, have a good day, and I'll see you on the next video. Bye-bye.